Welcome to the Civi 381 laboratories. Today we'll be giving a step-by-step guide on the constant head permeability test. The objective of this lab is to determine the permeability of a given soil using both hydraulic gradients in the upward and downward directions, as well as determining the hydraulic gradient at which the soil undergoes the quick condition. Just a quick safety note before we get started. Remember to wear your steel-toe shoes and your safety glasses in any geotechnical lab. So this is the configuration for the downward hydraulic gradient. First off, we have a water source, which is hooked up to a constant head source. Notice you have an overflow tube to make sure it's always at that constant head. The constant head is supplied to the top of the manometer, hence why we've got a downward hydraulic gradient. The water flows through the sample and out this discharge port. We also have two manometers. The upper one is hooked up to this manometer, and this guy, the lower one, is hooked up to this one here. We also, when we're measuring for hydraulic gradient, we want to measure from a datum. It'll be the countertop table. The total head at the top of the sample will be the distance from the countertop to the water line here. That's the total head at the top of the port, or at the top of the sample. The discharge port, the total head will just be simply the distance from the countertop table to that port. And then the head of these two ports will be the distance from the table to wherever the water lines are in the respective manometers. Now, you really don't need to measure from the countertop in these cases because we can simply take the difference between these two manometers and you should be able to calculate your head difference at those two locations. You also want to measure the distance, the length of the sample, and the distance between these two manometer ports. With all those measurements, you should be able to figure out what your hydraulic gradient is. But now we need to figure out what our seepage velocity is. So we're going to take a graduated cylinder and a timer and see how long it takes up to fill the graduated cylinder to some predetermined amount. Now be sure to take the temperature reading because we will be accounting for the viscosity of water. All right, so you're going to want to make those measurements 3 times. Water quantity as well as manometer readings, you're going to do that 3 times as well as the temperature readings. And then what you're going to do is you're going to lower the constant head tank 1 more level, and you're going to repeat the process. So you'll be able to get different values at different gradients, and this should allow you to determine what your permeability is, at least in the downward direction. So this is an example of lowering the total head, and you'd redo all the measurements. The configuration, honestly, is almost exactly the same. You just have to remeasure the distance from the table to the water level here. All right, so we're going to be setting up the permeometer for a upward gradient. We want to make sure that the gradient that we're setting up is going to be less than 1, probably around 0.5 or 0.6, to make sure we don't quick the sample right away and ruin the sample. We'd have to redo the whole test. So we're going to be switching these ports right here. The total head at the bottom will be the distance from the table to the total head here. It's a little backwards, I know. And the head at the top will be the distance from the table to here. So you make all those measurements and make sure that your hydraulic gradient is less than 1. This is the configuration for the downward or the upward gradient. When you change the ports, you might have some issues with air bubbles being trapped. Ask your TA for help. They'll be able to help you. The distance from the countertop table to the head level here is actually the head at the base. And then the distance from the table to this port is the head at the top of the sample. So everything's just reverse. I know it's a little confusing. You're going to repeat your steps for measuring water, temperature, and reading the manometers, and you should get your permeability in the upward gradient. Now, the other objective is we want to figure out at what gradient the sample is going to undergo the quick condition. So you should calculate or figure out at what height this should be at to incur a gradient of 1. And then right around there is where your quick condition should happen. If it doesn't, just keep lowering your sample until that occurs. We'll give you a close-up right now on what that should look like. To determine the permeability of soil, we're going to be taking a regression approach. We're going to be taking a linear regression between your your discharge velocity and your hydraulic gradient. So the equations are all here for you in the slide. Your discharge velocity is calculated by Q divided by TA, where Q is your discharge quantity, which is what you gathered in the graduated cylinder. T is the time it took to do that, which you recorded, and A is the cross-sectional area of the permeameter. And we're going to plot all of these points on the y-axis. I is your hydraulic gradient, which is the difference in total head divided by the length over which that difference in head occurs. These were all recorded in the laboratory, so this shouldn't be a problem to calculate. And once you have all these points, you can plot them on the x-axis, take a linear regression, and the slope should be your soil's permeability at that specific water temperature. Now the permeability will change based off of the viscosity of water, and viscosity of water changes with temperature. So we're going to want to correct it for 20 degrees Celsius. So the third equation says the permeability that you found times the viscosity of water at the temperature at which it was measured divided by the viscosity of water at 20 degrees will give you the soil's permeability at 20 degrees Celsius.